Let's talk about really common functions that we see, or very common time complexities that we see with big O notation. So one of the first ones that I'm going to mention is this one, big O1. This is just called constant time. And constant time means that no matter how big the data set is that this function is operating on, it always takes the same amount of time. This doesn't mean that it only is one operation. It means that it always takes the same amount of time. So a graph for this, where you have the size of your input and then you have the time, is going to look something like this. It's the same amount of time no matter how big the size of your input gets, right? This is something like if you're returning a single value, or if you do like a bunch of different math, it could be like 20 or 30 operations, but that function always takes the same amount of time to execute. Right? Another one is O log n. This is a logarithmic. Let's see, I'm going to spell this right. Logarithmic. Logarithmic functions typically do something where they split the size of the data at each step through the process. So if, for example, if you had a bunch of data, a vector of data, and you knew that you were searching for a value on the right side or the left side, right? And you could kind of chop this data in half and then go here, and then chop this data in half, and then go here and chop this data in half, right? And you are decreasing the size of your data with each iteration in half. You will create a logarithmic runtime. Part of the reason why this is logarithmic is because if you imagine that you have 100 elements in your size, in your container, in your whatever, in your input, and then you double it, it's only one more iteration for your function to just chop it in half. So really adding a whole bunch more data doesn't have a large impact on the runtime of this function. Logarithmic functions are something really to strive for because they are so incredibly fast, especially once you get to larger data sets. The difference between 1,000,000 elements in your vector and 2,000,000 elements in your vector is almost nothing. It's the difference between one element and two elements. Doubling the size of your data has such a little performance impact. These functions are really great, really fast. Another really common one, big O of n, right? N, remember, represents the size of our input. So as the size of our input goes up, this function goes up at the same rate. This is linear. If you were to graph this, the size versus the time graph, it would look something like this. Right? Remember, there's no indication of the angle of this thing, right? This function is also linear, right? It's worse. This is a worse linear because it's getting real bad real quick, right? This function is also linear. It's a better linear, right? Because it's, not getting too bad, like really quick. But these are all linear functions. Remember that linear functions could also theoretically start somewhere up here on the side. If you do a bunch of operations first, it's not always going to take a time of 0, right? So it could look something like this, a graph that starts up here and then shoots off from there. Linear time. This is something like, the really easy example is just a for loop that iterates while I is less than size, right? If you do this and you're looping while I is less than size, then every time you add a new element, you're adding another iteration in this for loop. So as your size gets greater, your overall function gets greater over time, right? Based on the size of this input. You double the size of your input, this function is going to take twice as long to run. That's pretty much what it comes down to. Another one, n squared. This is called quadratic. Quadratic looks something like this, where it's going to increase dramatically. When we have our size and time graph, it's going to increase dramatically. This is a for loop inside of another for loop, something like this. We have for while I is less than size, ... and then inside that you have something that's like a for loop j, and while j is less than the size, right? I apologize for my terrible handwriting. And then in here you could be doing something where you're comparing I bracket a bracket I bracket j to something else, right? This is going to increase in quadratic time. It's going to get worse. As you add to the size here, not only is it causing more iterations in this outer for loop, but it's also causing more iterations of this inner for loop. You double your size, and it doubles this outer for loop. But it also doubles this inner for loop. And so every time this outer for loop is running, it's also running this inner for loop. So it's actually getting really, really bad, really, really quick. So this is not a great function. This is a really, really, really slow function. Right? There's also a whole bunch of other ones, right? You may see something that's like n to the c, where c is some other type of constant, right? This is polynomial runtime. You may see something like this where it's like n exclamation point, right? This is factorial. This is really bad. There are some functions that have like a factorial runtime. These are terrible, right? You essentially want to avoid these at all costs. The real common ones are these: constant, logarithmic, linear, quadratic, and polynomial. There's a couple other ones that you find there as well. Big O of n log n, which there may be a couple like algorithms that we run into as well. I don't know a really good name for this one, actually. I think it's actually called something like log linear or something along those lines, because it's really just saying, well, it's linear times log or linear log or something along those lines. So I don't know, there's a bunch of confusing names for that. Most of the time, I've never met a programmer who calls this anything other than n log n. N log n. So you will hear other programmers talking about this where you say like, oh, that has a constant time complexity or a linear time complexity, quadratic time complexity. That runs at n squared. This runs at log n. This is all really common phrasing for programmers when you're talking to each other. So this is sort of the chart that you want to have in your mind, that you want to have sort of memorized. You want to learn all of these things. You want to learn which ones are faster and slower than each other. You want to be able to have these discussions with other programmers where someone says, oh, that's a logarithmic function or that's a quadratic function, and know which of those is a better choice. Right? Following up on this, we're going to talk about some of the really common functions that we use all the time, especially in our data structures, our vectors, our linked lists, and some of the other ones. And then also going forward, whenever you talk about functions, you should be using this. You should be using this terminology. This is how we compare functions to one another. This is it. Big O notation. This is how we talk about times complexity. This is also how we talk about memory. When you talk about, that has a linear memory complexity, that means that as your function gets larger, right, as the size of your input gets larger, the amount of memory that your function is going to take up gets larger. Right? So you may think of this as like a vector. As that thing increases, it's the amount of memory this is taking increases as well. So big O notation, start using this. Start using it all the time, right? You want to use this in all your functions. Whenever you look up the documentation of functions online, you'll see this sort of thing. You'll see a linear time complexity, quadratic time complexity. Any well-documented function online in any of the common data structures that you use or any of the common algorithms that you use will have the time complexity listed in them, right? For this exact reason. It's there so that you can make good informed decisions on which ones you want to use.